To last workshop of the semester. We've got kind of a fun grand finale planned for these last two. We're talking about transformers. Now, those of you who were here last week saw a little preview of transformers. We were talking about ChatGPT and the brand new GPT-4, which are sort of the current state-of-the-art, like craziest brand new stuff going on in AI right now. I think basically everyone here has probably tried or seen ChatGPT at least once. But it's this amazing text-based AI that can do a lot of general text tasks that we really haven't seen before. And like we were saying last week, I think now it's probably been like 13 days ago, GPT-4 came out, and it's the most impressive AI thing anyone has ever created in the history of humanity. And so it's really a crazy time, and transformers are sort of the key underlying idea that are giving us all these new AIs. Everything new that's interesting that's going on in this world in text processing is happening because of this model structure called a transformer. And so they really are transforming everything. And it's just a fantastic time to be in AI. Literally on my way here, walking to the STEM building, I was listening to a podcast episode with Sam Altman, who is in charge of OpenAI, the company that's making this ChatGPT stuff. And it's just crazy to hear about the rate of development and the way that things are going. And so we thought for the last two workshops of the semester, we should focus on transformers because this is where everything is happening. Like, this is the moment for transformers in human history. And so it's really cool that we get to talk about them here. And actually, all of the things that we've done so far this semester have sort of been building up to this moment. That we talked about multi-layer perceptrons, we talked about CNNs, convolutional neural networks, we talked about RNNs, recurrent neural networks, and these are all getting closer and closer to helping us understand transformers that are going to be these incredible text processing things. If you'll recall, these are the different types of neural networks we've looked at this semester, ending with recurrent neural networks. And when we introduced recurrent neural networks, we said, hey, this is the way that you do text processing, or the way that you deal with sequences of data. Text is just sort of a sequence of words, or maybe tokens. We are going to kind of cross that out and say, you know what? Recurrent neural networks are great, and they do work, but transformers are our new best friend. Transformers do essentially the same job, which is dealing with sequences of data, but generally, they do it better. And so for that reason, our friendship with RNNs is ended, and transformers are our new best friend. So we really want to talk about transformers, but before we get there, I think it's worth doing just a little bit of history to sort of see how we got here before we jump into what exactly the innovation behind transformers is. So Uzera will tell us a bit about the history of text processing.
So like Josh said, this is a very historical week in AI, just the last couple of weeks. If you just Google transformers, if you just Google AI, all of the headlines are about transformers, since early March. And I want to take a moment to look at how we got here. So this whole semester has been leading up to transformers. How do we go from MLPs to transformers? So language models have existed way before even machine learning had existed, before neural networks have existed. On your phone, autocomplete is basically your basic keyboard autocomplete is something called an n-gram model, which this is when people are starting to answer the question of how do you teach a computer to reason about text. The big idea was how do we automate this stuff, and obviously these have a lot of limitations. If you just keep clicking the first word on your autocomplete, you will generate pairs of words that are coherent, but the sentences will just come out to be nonsense. And later on, we have the innovation of the neural network. And the first person to propose this application to language models was Yoshua Bengio. And he introduced his paper, which used MLPs, which we learned about in the first week. But these are also pretty basic. And a further innovation later on were RNNs, which we learned about. These became widely used around 2010. and these handle sequences of text, as we learned about. And these also have a few limitations. We didn't talk about this much last week, but these are really important limitations. They're very slow to train, and they don't work very well when you have really long pieces of input, because it suffers from something called the vanishing gradient problem, which basically means that it doesn't remember things from long ago in its input. And Josh is going to talk about another example that kind of motivates the idea of what we're going to talk about next.
Yeah, so for the past few weeks, we've talked about RNNs, recurrent neural networks, which are pretty good at processing sequences of data. But sometimes language is a little too complicated and a little too nuanced, and I want to show you a good example of that. This is a sentence. Take a second to read it. It says, "The monkey loved to play with the balls, but ignored the blocks because he found them exciting." What is "them" referring to in this case? We actually have some disagreement. I've heard both blocks and balls. It's not 100% clear, but from context, you might say, well, the monkey finds them exciting. And so it's like, well, what is them? He loves the balls, but ignores the blocks. So if he finds them exciting, he's probably talking about the balls, because the balls are the thing that the monkey finds exciting, right? On the other hand, if you have the exact same sentence, but you change the last word to be dull, you say the monkey loved to play with the balls, but ignored the blocks because he found them dull. This one's maybe a little clearer. Them is referring to the blocks, because he's ignoring the blocks, since the blocks are dull. And so this one word in the sentence makes a big difference to the word them, right? Them could be referring to balls, it could be referring to blocks, and which one it is depends on actually the next word in the sentence. And so with our old recurrent neural network model, where we said, hey, we're just going to sort of go along and update our mental state about how the world is as we move along and read word by word, it can't really do this. What we want is some way to say, hey, when I'm looking at a word, like the word them, I really need to be able to go back and reference particular other words in the sentence. So in this case, you really want to reference the word balls, reference the word blocks, and reference the word either exciting or dull. And so the key innovation behind transformers was a concept called attention, where as you're reading, you can sort of pay attention to certain parts of the input that are most interesting right now. So we're going to talk a little bit more about that, but that is sort of the key concept.
So later on, we have the idea of attention, which is what Josh has talked about, and it's inspired from an idea that we're all familiar with. It's how we intuitively understand the world. When we look at a picture or read a sentence, we don't pay attention to everything at once. We kind of focus our attention onto the relevant details. And you can see an example in this image, which came from the first paper that kind of introduced attention, and it was in the context of image captioning, where the model learns what are the important parts of the image, and then it generates a caption accordingly. For example, on the top one, it's highlighting the frisbee and underlining the frisbee. And this, when you apply this, you can apply this to recurrent neural networks. And later on, we came up with the transformer, which is basically just pure attention applied onto the input. There's a few other parts, but the main idea is attention, the attention mechanism in the transformer. And these transformers, it's a very subtle difference, but these have huge implications. This basically went from making R9s and MLPs completely obsolete in most applications, and they're surprisingly versatile. You can use them on any application. You can use them to classify images and generate text, classify text, and do pretty much anything. And they're faster to train, and you can use massive data sets on them. And yeah.
Yeah, so as Uzair said, really the key innovation here is attention. And you can apply attention to recurrent neural networks, but transformers sort of take this idea and make it the core of how the transformer works, rather than being a thing we sort of tack on later. There are lots of other details to how a transformer is designed. We were talking this week with Morgan, our graduate advisor, and he was saying, man, all the other details, it's like, they're kind of just made up. Like, it's a lot of random stuff that people don't actually know exactly why it works. There are details we can go into, and maybe next week we'll talk more about the design of the transformer in particular. We're not going to cover all those details today because A, they're not super well understood in general, and B, it would just be too much to talk about all in one day. So we're really just going to focus on this idea of attention. And we can go back and fill in more of the details of how transformers work later. But the key idea is that transformers are built around attention. So this diagram is an example of self-attention. It's called self-attention because you have the same sentence on the left and the right. The monkey ate that banana because it was too hungry. And the idea is that as I'm looking at the word it in the sentence, I want to find which words are sort of correlated or which words are interesting to pay attention to as I'm looking at the word it. And so it could correspond to the monkey, or it could correspond to the banana. And so you can see, in this case, actually, it does refer to the monkey because the monkey is hungry. And so the monkey, those words are sort of most intensely highlighted, whereas banana is sort of a potential candidate for what it could be. But it's not quite as strongly highlighted. And so the idea is that for each word in the sentence, we're paying attention to other words in the same sentence. And because it's the sentence referring to itself, that's why we call it self-attention. We're not going to get into the details, the real nitty-gritties of how you select which words to pay attention to. But what I will say is there's this concept of a query and a key. And sometimes when people talk about this, they use an analogy to databases, where if you've ever had a database, maybe you have a big table full of data, and you make a query, and you say, I want to find all the rows where this value is greater than or equal to 5, or values that have this word in a particular column, or things like that. You have a query, and then each sort of row in your database has some data. It has keys that you can search through. In this case, the way it essentially works is for every single word in the sentence, okay, by the way, little side note, I keep saying word. What I really mean is token, and we've talked about in previous workshops the subtle difference. I think it's easier to think about it in terms of words, but usually it's actually tokens, which are slightly different, but pretty similar. Anyway, for each word, as I go through, I'm going to assign each word two things, a query and a key. The query is basically a search term. It's like if you go into Google, it's the thing you're searching for. And so it is searching for what it refers to, right? It's searching for a thing that it could be. Each word also is assigned a key, which describes what I am, right? So the monkey, the key will sort of say, I'm a monkey, right? The key is a mathematical vector that's supposed to describe what the word is. So for each word, you have what it is and what it's searching for. And then you essentially just do a dot product to compare. And so for the word it, you have some query, right, which is just a bunch of numbers. And then for each word in the sentence, you have a bunch of keys that describe what those words are, essentially. And the goal is to find keys that match up well with the query. So you're trying to find words that are the words you're searching for, essentially. And so this query key idea is how attention works. You're saying, in the neural network, you're training this matrix that helps you assign to every word a query and to every word a key, and then you just go through and find which words match my query, which words have keys that match my query. And that's how you pay attention to the most interesting words as you're going through and reading this sentence. And that helps you solve the kinds of hard problems that we had earlier, like this one. So this also works, this again was self-attention, where the sequence was sort of paying attention to itself. It was looking at other words in the same sequence. This also works for tasks like translation, where rather than having just one sequence, you actually have two different sequences. And if you're doing a translation task, generally what happens is, you can sort of imagine a naive translator would just say, okay, I'm going to take an English sentence, and for every word, I'm just going to turn that word into the Spanish equivalent. But it's not really that simple, right? One word in English may be multiple in Spanish, or maybe I flip the order around. And so what you really want is to be able to represent how the words in the original sentence correspond to the words in the new sentence. And so again, we're looking at, in this case, we had a correspondence between words in a sentence and other words in the same sentence. Here, we want a correspondence between words in one sentence and words in a different sentence. And this diagram shows an example of that. Here I'm going from French to English. Now, I've never learned any French, so I don't know how to pronounce these things, but you can see it's the same sentence in two different languages. And we have this very interesting diagram going on where it looks like mostly a diagonal line, but there's this little slice through it of three sort of words where the diagonal is going in the opposite direction. And it's worth thinking about what exactly is going on here. Maybe I can highlight the interesting area. This matrix, this sort of pixel picture, is showing the correspondence between different words. So again, it's showing the attention. And every single entry is showing you, well, how do the words in the French sentence correspond to the words in the English sentence? And the key thing to notice is that in in English, I'm saying European Economic Area. And then in French, I'm not even going to attempt, I'll butcher it, but the zone, which I guess is area, économique, or whatever, is economic, and then whatever the French word for European is. They go in the opposite order. Right, I have zone economic European versus European economic area. And this diagram is showing me how, as I generate my English sentence, I'm paying attention to the French words in the reverse order. Those three words flip around. Everything else basically goes in the normal order that you would expect. But as I'm generating my English, I look at those three in reverse order. And a recurrent neural network can't do that. Our normal recurrent neural network just basically goes from the beginning to the end. Sometimes you have a recurrent neural network that sort of goes both ways at once. You can try to get fancy with it. But this idea of attention really helps us to skip around and pay attention to different things as we go. So transformers are built on this idea of attention, where I'm going to look at correspondences between words. And they really just apply it hardcore. The original paper that introduced transformers to the world was written in 2017, and it's titled "Attention is All You Need." And they essentially created a network that had 6 layers of attention, and they had an encoder and a decoder. There's a whole setup, but they had 6 layers of attention going on. It was like attention on attention on attention, and it really was this idea that attention is all you need. And it turns out there's more structure built up around it, but for today, we are going to go with that reasonably simple idea of attention is the key idea. I care about the way that words correspond with each other. Now, I have a few fun facts about transformers for you. One is that transformers, unlike RNNs, are super efficient to train. We mentioned attention as the key idea, but one of the other things that transformers do really well is they're able to be trained very efficiently because it can happen in parallel. With an RNN, if you remember how it worked, we would essentially look at the sequence one word at a time. So we'd look at the first word, look at the second word, look at the third word in order. And because it's happening in sequence, that's really hard to make go fast. I don't know how many of you were here when Dr. Colbury did a presentation about doing stuff on the GPU and using the supercomputers here at MSU. But one of the key ideas was, if you can have a task that can run in parallel, where you can do lots of separate computations all at the same time, you can do it on a GPU, which is optimized for that, and it'll go really quickly. Because if you have a big supercomputer, you can just run 10,000 computations all at the same time on separate physical components, and then just gather up the results. And because transformers don't go one word at a time, reading from beginning to end, or from end to beginning, they actually jump around. they're sort of built in a way where each word can do its own computation on its own, independent of the other words, and so you can process the entire sequence all at once. And so that makes them very efficient to train. Another really fun fact, I think this might be my favorite fun fact about transformers, is nobody really knows how they work yet. This is from a paper about transformers. I don't remember exactly what it was called, but this paper... GLUs, okay. People were playing around, these scientists, right, real experts in the field were playing around with designing different transformer models. And they found some designs that worked better than the alternatives. And what they wrote was, we offer no explanation as to why these architectures seem to work. We attribute their success, as all else, to divine benevolence. We really don't know how this works or why. We don't know why this is a better transformer design than others. And so even the experts in the field, certainly they understand some things. There are things you can learn about how transformers work, but we as a